This section revisits the foundational concepts that define the definite integral, Riemann's sums, and their limit. Understanding this is crucial before advancing to sophisticated integration techniques. Imagine finding the area under the curve y equals f of x between x equals and x equals b, where f of x is continuous and non-negative. A Riemann sum approximates this area. Here's how. First, partition the interval from a to b into n subintervals using points of equals x0 less than x1 less than x2, and so on, up to xn equals b. The width of the ith subinterval from x sub I minus 1 to x sub I is delta x sub I equals x sub I minus x sub I minus 1. Often, regular partitions where each delta x sub I is the same, delta x equals b minus over n, are used. Next, choose a sample point within each subinterval, often denoted x sub I star, such as the left end point, right end point, or midpoint. Finally, form the sum of areas of rectangles built on each subinterval. The sum r sub n equals the sum from I equals 1 to n of f of x sub I star times delta x sub I. This sum, r sub n, is a Riemann sum. It represents the total area of the rectangles approximating the region under the curve. The approximation improves as the number of subintervals n increases, and the maximum subinterval width, written as the norm of delta x, approaches 0. The definite integral of f of x from a to b is defined as the limit of these Riemann sums. The integral from a to b of f of x dx equals the limit, as the norm of delta x goes to 0 of the sum from I equals 1 to n of f of x sub I star times delta x sub I. If this limit exists, which it does for continuous functions on the closed interval from a to b, then f is said to be integrable on that interval. Geometrically, for non-negative f of x, this integral represents the exact net area between the curve and the x-axis over the interval from a to b. Definite integrals obey essential algebraic rules vital for computation and manipulation. First, linearity. The integral of c1 times f of x plus c2 times g of x from a to b equals c1 times the integral of f of x plus c2 times the integral of g of x. Second, additivity over intervals. For a less than c less than b, the integral from a to b of f of x equals the integral from a to c of f of x plus the integral from c to b of f of x. Third, order preservation. If f of x is less than or equal to g of x on the interval from a to b, then the integral of f is less than or equal to the integral of g. Fourth, reversing limits. The integral from a to b of f of x equals negative the integral from b to a of f of x. Fifth, the integral of a constant. The integral from a to b of c dx equals c times b minus a. While the Riemann sum definition provides the core meaning, the fundamental theorem of calculus, which is covered next, furnishes the primary tool for actually evaluating definite integrals. Mastery of this limit process and integral properties is essential for understanding advanced integration methods. Review of Riemann sums and definite integrals is just one small part of Calculus 2. If you are interested, our full free Calculus 2 course is linked in the description.